I just wish.
All right, so I think we can start. So hello everyone, welcome to this very first webinar dedicated to James Webb. So I'll introduce myself. I'm Julien Rameau. I'm at the University of Montreal and I will be one of your point of contact in Canada to help you design your proposal for James Webb. I will also introduce Loïc Albert, who actually is sitting next to me, who is the second person to help you to design your proposals. So the goal of these webinars is to help you masterize the James Webb as a world facility. So we'll introduce the different instruments and the different survey modes, but also all the tools that have been developed in parallel to the facility to design observations with the different instruments. So in the end, after those webinars, you should be able to be very well prepared for submitting a proposal for the next call. So we designed a series of 8 webinars. So the first 2 will be very general. So the first one will be, so today will be dedicated to the presentation of the different instruments and observing modes. And the second one next week will be dedicated to the tools that have been developed to help you design your proposals. And the next 6 webinars that will be given over the next month of December and January will be specifically focused on specific observing modes. And the particularity of this webinar will be that we'll be giving live demos of the different tools. And we will go through each step to design a proposal with you. So we encourage people to play with the tools in real time during the webinars. So finally, I would say that we will record all the webinars using the Zoom system and we'll post online those webinars with all the material that we have been developing for those webinars on the website right after the seminar. So I encourage people to check this out and to go back as often as you need to help you design your webinar. So today is the very first webinar so dedicated to the James Webb in general. So it will be given by René Doyon. So I like the screen to run. Thank you and enjoy.
Oui, un instant.
Okay, good afternoon, everybody. So may I ask people just to mute themselves to make sure that we don't have any background noise. So you just go to the lower left of your screen and there's a mute button. Okay, so as Julien explained, first of all, I guess you can all see my screen. I just want to make sure that everything's fine.
Yes.
So as Julien mentioned, the purpose of these webinars is to get you acquainted with JWST, and hopefully will convince you that you should write a proposal for JWST. So just to give you a brief update of where JWST is. So this is a picture of the telescope when it was tested before it got into the big chamber in Houston back in July of this year. And since then, the telescope and all 4 science instruments have been thoroughly tested. And in fact, this is now done. This is checked. These pictures just show you the main components of JWST. You know, this big mirror, 6.5 meter telescope, the sun shields that protects the telescope from the sun all the time. So the telescope is always in the shadow of the sun. And on the back, the spacecraft. So right now, the focus is very much on the final integrations of the spacecraft and the sun shield. But basically, the top one, the telescope, is essentially done. Okay, so my outline is that is to give you an overview of JWST in terms of you know, the instruments, the science program that we're going to do with them. So I'm going to go through all 4 science instruments with example of science programs that will be done with JWST, and very briefly an introduction to what are the steps towards writing a JWST proposal. Okay, so let's dive into it. So first of all, just a general timeline of where we are. So first of all, the launch is now scheduled for the spring of 2019. So where we are is we're 2 days ago, there was the early release science. I will talk very briefly about that. So early release science are sets of observations that will be done early in the after launch. And those are community programs with no proprietary time. And these are data that will be available to everybody. So those programs are now available on the web. You can go and find them. An important date will be in 2 weeks, November 30th. This is the cycle 1 call for proposal for general observers. So there you see all the details of what you have to do to prepare proposals. And a very important date, this is April 6th of next year, which will be the deadline for the cycle 1. And the time allocation committee will follow about a month after, maybe in June, to determine. There may be a delta call for proposals, but for now this is not yet approved. But we'll know in 2 weeks when the Space Telescope Science Institute issued the call for proposals. Okay, so this table gives you the time distribution in cycle 1. There's various acronym here. You have to get used to it. So GTO stands for Guaranteed Time Observation. So this is the time allocated to the instrument teams and various people. And by policy, there cannot be more than 50%. I'm sorry. So 50% of all JWST's time has to be in general observers. So proposal that you, for example, will submit. So GTO for now amounts to something like 2,800 hours. Early release science, as of yesterday or last Monday, there are 13 programs that have been selected. Programs that exercise all four science instruments and a wide variety of science programs. And that amounts for 460 hours. So basically what this is director discretionary time, DDT, which normally is 10%. So in total about 800 hours. So there will be something left, about 416 hours of DD time. So after all proposals that have been approved during the cycle 1, if you have an incredible idea and you'd like to submit, as usual, you can submit a DDT proposal to the director to get your time. So that corresponds to 10%. And so early release observations, that corresponds to the very first observations and data that will be acquired by the observatory. So for public release, for public relations, and just to show off what the observatory can do. And there's about 80 hours there, about 20 hours per instrument to show what JWST can do. And finally, the time that matters to you, this is the general observers. There's about 4,000 hours overall for the JWST project. And the notional share of Canadian geo time is 5%. So on cycle 1, that corresponds to about 200 hours. I put greater than here because it's a minimum. If we Canadians are competitive enough, we could get more than this share. And one very important message I want to get across here is that the Canadian Space Agency will actually fund GTO and successful geo proposal for science support. So if any successful geo proposals will receive money from CSA on average at the level of about $1 million a year. You're not going to get that amount, but that gives you an idea so the bottom line is if you're successful at getting time with JWST, you will get money from CSA with it. The details of this funding will be provided by CSA early January 2018. Okay, we can take questions right at the end, but if there's any urgent questions, you can always unmute yourself and ask the questions. So otherwise, this slide here is taken from a teleconference last Monday, and this is a courtesy from Nicole Lewis from Space Telescope Science Institute. And that gives you a breakdown of the ERS proposal. There were programs that were approved. So there were 106 proposals that were submitted for a total of 3,600 hours. So you can see there was a factor of 8 pressure for the 450 hours that were allocated. There's a breakdown by countries. So there were 4 from ESA, 9 from US, and various countries. So you can see there the statistics for Canada. There was only 1 proposal with a co-PI from Canada, but there's also co-Is. So Canadians represent about 3% of all co-Is in the ERS proposals. So you can go on the web and get these proposals to see the details of their program. You just have to follow that link. Okay, now let's move on to the actual details of JWST. So one very first important point to mention is what piece of sky JWST can see at any one time. So JWST is at the second Lagrange point, 1.5 million kilometers away from the sun. So the telescope is always following the Earth around the sun. And as I said, the telescope is always in the shadow of the sun. So there's this region that you can see all the time. So you can actually go look at that is the ecliptic pole. And that's the northern one, the southern one. And you can rotate the observatory up to plus 45 and minus 5 degrees, so about 50 degrees. So it's typically about 40% of the whole sky is available at any one time. Of course, if you want to observe on the other side, you have to wait, later towards the 6 months later. And this region here is very important. This is the continuous viewing zone. That's a region you can always observe all the time throughout the year. Okay, so that translates into this plot. This gives you the target visibility in days per year as a function of ecliptic latitude. So something that is on the ecliptic will have limited visibility, typically approximately 53 continuous days twice a year. Above about 45 degrees of ecliptic latitude, then your target is basically visible for a long period of time, given by this graph. So all the way to the CVZ, which is about 10 degrees at about 85 ecliptic latitude. Okay, one very important aspect of JWST, it's wavelength coverage. It's very broad. It covers from the red visible 0.6 to 28 microns. So this diagram just shows the actual overlap with the existing space telescope, HST, and Spitzer. So the telescope is Nyquist sample, so that the diffraction peak is actually, the telescope is diffraction limited at 2, 4, and, well, it is diffraction limited at 2 micron, but the instruments are sampling that PSF with a Nyquist sampling that is 2 pixels per lambda over D at 2, 4, and greater than 7 micron. Okay, now let's move on to instrument and science program. So first of all, just to give you the main science theme that JWST will address, well, as you can guess, it will cover essentially everything from the early universe to understand the first light and the reionization epoch, galaxy evolution called galaxy assembly, and the birth and stars and protoplanetary system, so basically star formations and disks, and finally planets and the origin of life, which include in this solar system science, exoplanets, so a very, very broad science programs that JWST can do. Okay, so there are 4 science instruments, and NIRCam, NIRSPEC, FGS, NIRISS, and MIRI. And what you see here is the actual footprint of each instrument on the sky. And I will come back to that later very briefly. It's possible to use more than one instrument at a time to do parallel observations. But basically, each instrument has its own piece of sky that it can look at. Okay, so this is how this hardware looks like before they were actually put behind the telescope. That gives you an idea of the scale of this big of these instruments. So they're now fully integrated and functional. So in terms of sensitivity, these plots just show incredible improvement that JWST will have over existing facilities. So on the left, this is the photometric performance for imaging point sources. Noise of 10 in 10 to the 4 seconds. And you can see the incredible improvement that JWST will provide at some wavelength. This is several orders of magnitudes that translate into the square of that in terms of telescope time needed to achieve these flux levels. On the right, this is a similar plot, but for spectroscopy, low resolution spectroscopy, and medium resolving power. I just want to mention that JWST is not a high resolution spectrograph. The highest resolving power would be about 3,000. That's really geared towards doing galaxy dynamics. And you can see that at longer wavelengths, JWST will have several orders of magnitude improvement in sensitivity. So a huge discovery space. Okay, all these 4 science instruments can do basically 2 things: imaging and spectroscopy. And imaging comes in various flavors. Of course, standard imaging with filters that NIRCam and MIRI provide. But there's also coronagraphy, high contrast imaging, that are specific to 3 instruments. And NIRISS has a very special mode called aperture masking interferometry, which I will very, very briefly talk about. But we'll have a dedicated webinar after Christmas on coronagraphy and aperture masking interferometry. For spectroscopy, you can do multi-object spectroscopy, single-slit spectroscopy, integral field spectroscopy. That is a small region of the sky where every pixel gets a spectrum. And basically, all science instruments has these capabilities. Well, not all. For example, NIRISS cannot do IFU. Just another plot to give you the resolving power that you can have and the wavelength range for various wavelength range. So just to show you that there's several modes you can choose to do. And this is color-coded by various science instruments. One mode that is worth noting here, this green mode here, it's a low-resolution mode that NIRSpec provide a spectrum from 0.6 to 5 micron in one shot at very low resolving power, about 100. It varies from 20 to about 200. And depending on your application, you will want to choose maybe something different, high resolution, medium band resolution, which of course gives you a more limited wavelength coverage. So depending on your application, you'll have to choose among these various modes. Okay, now let's move on to the first instrument, the NIRCam, which is anticipated to be the workhorse imaging instrument from 0.6 to 5 micron. The picture here shows you how it actually looks like. Basically, NIRCam provides standard imaging. It covers, in fact, it has 2 channels, channel A and channel B, and they are fully redundant. And there's a dichroic mirror that sends all the blue light from the short wavelength channel from 0.6 to 2.3 micron, and the long wavelength channel to 2.4 to 5 micron. So the footprint you see here, for example, the blue are basically one detector, short wavelength detectors. There's 8 of them, okay? And the red one is the long wavelength detector. And the pixel scale is such that the long wavelength channels cover the whole size instrument. It's basically because the telescope is NACWA sample at 2 micron with 32 milliarcseconds, whereas at 4 microns you can double that. So essentially, when you take an image with NIRCam, you're getting all that. You're getting all these 8 images on both channels, and also the detector is simultaneously at a different wavelength. So this is a very powerful capability. The coronagraphic mask, as you see here, can be optically inserted into the detector with a little prism through a mechanism, and this is how one can do coronagraphy. Okay, so here this is the actual filters that NIRCams can have. The main one you will probably use are those one here, the white filters. These are typical filters, bandpass of R equal 4, R meaning delta lambda over delta lambda. These filters were really designed to do photometric redshift and for finding high redshift galaxies. The numbers refer to the actual wavelength. So 115W, that's at 1.15. That's 1.15 micron. And there's also a suite of median band and narrow band filters for various species. So you can do imaging of through all these filters. The long one here I use for other applications like GRISM spectroscopy. I won't go into these details now, but that's the kind of sensitivity that NIRCam will achieve, which is compared to what you would do on an 8-meter telescope on the ground. That's a huge improvement, orders of magnitude. Okay, just a plot showing you a performance of the NIRCam coronagraph. And so this is a contrast curve versus separations. And we're showing here, so typical planets like Beta Pig B, the HR 8799 planets. And this is the sensitivity, the contrast that NIRCam should achieve with some reference BSF. And basically, JWST is not designed to do high contrast imaging, but it will have a lot of power to detect faint planets at relatively large separations. Okay, here's a science example with the GTO program, which is combined between NIRCam, NIRSPEC, and MIRI. I will talk about this instrument later. This is to do a deep survey to understand galaxy evolution and find the highest galaxies in the universe. And you can see all these footprints are basically the NIRCam footprint in orange. And the others are NIRSPEC and MIRI. So all three main science instruments will actually look at this field. These regions here are actually parallel observation. So while say NIRSPEC or MIRI is observing is prime, there will be also parallel observations taken with NIRCam. Okay, NIRCam can also do GRISM spectroscopy. So basically, you can insert a GRISM into the beam so that every source in your field of view is turned into a spectrum. There's no slit here, so this is what we call slitless spectroscopy. This is done at this resolving power, about 1,000, and over the long wavelength channel with NIRCam, 2.4 to 5 micron, with this kind of sensitivity. So and there's two of them with cross dispersion. This is useful for crowded region to discriminate one region to one source to the other. And this mode is also used for single object, in particular to do transit spectroscopy over that wavelength range. Okay, so here's an example of simulations of searching for high redshift galaxies, most specifically line emitters. So on the left here, this is a Hubble image of the Hubble deep field with C3 at 1.6 micron. On the right, this is a simulated image of the same scene, but at 3.6 micron, about 2 hours. And on the right, same amount of integration time, but with the GRISM. So you can see you're getting all these, the spectrum of all these sources. Okay, I mentioned that NIRCam has a lot of filters, medium band filters, and what you're seeing here is a spectrum of very low mass object. And just to show you that these medium band filters are very well matched to the expected SED, spectral energy distributions of very low mass stars and brown dwarf. And so for finding these objects, NIRCam could be a good machine to use. And of course, NIRCam, as I mentioned, can do transit spectroscopy using, especially with the GRISM mode. Okay, now moving on to another major science instrument, NIRSPEC. So NIRSS is built by ESA, the European Space Agency, in collaboration with NASA for the detector. So this is basically the main spectroscopy capability of the observatory. So NIRSS can do various types of spectroscopy. It has an array of what we call microshutters. So basically, let me show them to you here. So they look like this. These are little microshutter that have a tiny field of view, 0.2 by 0.5 arc seconds, that you can open in it, that you can open and close to actually define slitlets. So there are thousands of those here. And so basically, if you have a list of sources that you'd like to have spectra, then you can define with the microshutter the slitlets and take spectra. A slit spectrograph is much more sensitive than, well, it is more sensitive than slitless. And so this is a very powerful capability. And in that mode, you can operate with all the gratings that NIRSS have, from resolving power of 100 to a few thousand. So the pixel scale is 0.1 arc second. There are also fixed slits. So if all you care about, if your science program has only one object you'd like to look at, then you would use those fixed slits. And there's also a region here, the blue region, which is specifically for the IFU, the integral field unit. So basically, this is a region of 3 by 3 arc seconds where every pixel will actually get a spectrum. I'll give you an example of these things later. So overall, the field of view of NIRSS is about the same as NIRCam. It's not a coincidence. About 3.4 arc minute by 3.6 arc minute. And there's 2 detectors on the back of those microshutters. So there's always 2 for redundancy. Okay, this is just a plot showing you the actual a simulated image. Show you all the orders, not the orders, but the spectra that one gets, for example, with the IFU mode. I have already showed you this plot. This is basically the resolving power versus wavelength. Now this time just for NIRSS. And so basically you have these modes. The highest resolving power is with these prisms, and you can have medium resolving power, and finally the prism that gives you a simultaneous spectrum from 0.6 to 5 micron in one shot at R of about 100. Okay, so yeah, so basically you have 700,000 of these microshutters that you can dial in, that you can to define your scene, and of course all that is actually transparent to you. So all you have to provide is a list of sources. Ideally you would, well, not ideally, but in practice most of the time you will take first an image with NIRCam to see where your sources are, and then you will send a list to NIRSS to get that. But if you have already a good list of targets with good astrometry within 5 milliarc seconds, you can actually do right now multi-object spectroscopy with NIRSS. Okay, this is the actual sensitivity for the IFS, the integral field spectrograph, which is used specifically for extended and multiple sources. And it is used with the highest resolving power. And what you see here is basically the line flux sensitivity and the continuum flux sensitivity. But what you should remember is that this is a small field of view, 3 by 3 arc seconds, with a pixel scale of 0.1 arc seconds. And you know, it can look at fairly bright objects, J magnitude of about 5 to 7.5. Now, as I mentioned, NIRSS has also fixed slits, and those that what we call high sensitivity for single object spectroscopy is because the microshutter array is not perfectly opaque. There's a little bit of light leaking, but not a lot. But again, if you have only one object to observe, you better have to use one of those slits. So 0.2 by 3.3 is all those 3. There's a big one here, 1.6 by 1.6, which is actually the one used to do transit spectroscopy. To do transit spectroscopy, of exoplanet. It's ideally you don't want to lose flux in your slit, so the larger the slit is, the better. And ideally, you don't want any slit at all. Okay, so yeah, so that mode will be dedicated to time series observations, bright object time series that are optimized for transient spectroscopy. Okay, so here's an example of the IFU science. This is a GTO program to look at the moons Europa and Enceladus. You probably know that these moons have plumes, especially Enceladus with the Cassini mission that found waters. And so basically every square here will give you a spectrum. So this is 0.1 arcsecond. This is, as you can see, this is very well matched to sources like this one. This is Europa. And these contours were actually, these plumes were discovered by HST. And on the right, this is a potential spectrum that one could get out of this. So you can see the incredible information that the NIRSS IFS will provide. Okay, the core science program of NIRSS is to do this, is to do multi-object spectroscopy of high redshift galaxies. And this is a simulated field here. It gives you an idea of the kind of data product that you will get. In this specific case, this is using the prism, so the spectra are relatively small. And typically, one can get you know, as much as 100 objects in one setup. Okay, and all of that, and you will see later when we have a webinar dedicated to multi-object spectroscopy, this is transparent to you. So all you have to do is provide a list of objects and the software to actually design the actual observations that will take place for the various positions. Okay, an example here of the of IFU science with NIRSS. This is basically a galaxy, a lower redshift galaxy observed with the VLT, but redshifted at redshift 1. And so basically, and on the right you see spectra, and you can see the velocity structures. And just to show you that, in fact, the NIRSS IFU was really designed to do this kind of work. Here you're really looking after getting the dynamics of a galaxy in this kind of redshift range. And if you go on the web page for the ERS program, you'll see there's a lot of demand to do IFU science with NIRSS. Okay, just another example of a high redshift galaxy. This is a quasar here with, you know, emission lines, and it just gives you an idea. And that's at redshift 8, and you can see the noise is actually quite good. I don't have details about the observing time needed for that, but it's not all that much. And this, yeah, NIRSS will be an incredible machine for studying the early universe. And that's an example here where, you know, one would probably use the fixed slits because it's only one object, and you're seeing that you'll take the best sensitivity, the highest sensitivity mode for this. Okay, now moving on to MIRI. MIRI is the mid-infrared imager. MIRI has several observing modes. So this is the detector here. So on the right, this is the reason why you do imaging. And like NIRSS, there's little regions where you can do also IFU. And on the left here, this is all dedicated to coronagraphy. There's one, the standard LEO coronagraph here, and those are special coronagraph that we call the 4-quadrant coronagraph. I'm not going to go to the details, but all that region here is dedicated to coronagraphy. So the wavelength range is complementary to the other instrument, NIRCam and NIRSS. It goes from 5 to 28 micron. Nyquist sample at 7 micron with this kind of pixel scale, so 0.1 arcsecond per pixel. And there's also some fixed slits to do spectroscopy, and also in the slitless mode. Okay, just to show you that MIRI suffers from a lot of background, the actual zodiacal background from the solar system, but also from the telescope. There's a very strong component of background from the telescope, but still, you know, MIRI will be a very, very sensitive. I mean, that's the fundamental reason why we are cooling down the telescope to such low temperature, around 40 Kelvin. And in fact, the MIRI detector is cooled to even lower temperature, about 7 Kelvin. So I'm not going to go through the details of all this, but you can read them afterwards. But this is this kind of a saturation level that one has. And in fact, this is very bright. In fact, or this is very. What I'm trying to say is that a very faint source on the ground will actually saturate with JWST. So MIRI will be very sensitive and quite unique in this wavelength range. Just a simulation, not simulation, but measurements of the performance of the MIRI chronograph. So they can be used with these wavelengths, and so it gives you an idea about the field of view that the chronograph will cover, 24 by 24 arc seconds, and the performance here against contrast, 5 sigma contrast at that wavelength. MIRI LRS, which is for low resolution spectrometer, which can be used either slit or with or without slits. It goes from 5 to 12 microns. So this region here is with a slit, and there's a region here between the chronograph where you can actually you will get a slitless spectrograph. Okay, and this mode here will be used mostly for transit spectroscopy. Okay, as I mentioned, like NIRSPEC, MIRI has IFUs. In fact, it's actually 4 channels, so it covers the wavelength range from 5 to 29 micron. And if you want to cover this whole wavelength range, you have to do 4 observations. So all these, so you can see as you go to longer wavelengths, the field of view actually increase. So that gives you an idea of what MIRI will do. This is compared to galaxies. Okay, so like NIRSPEC and NIRCam, MIRI was really designed to provide a very important data point of the spectral energy distribution of high redshift galaxies. So this is very complementary to NIRSPEC and NIRCam, and so this is why the main JTO programs on high redshift galaxies includes not only NIRCam but also MIRI and NIRSPEC. MIRI science will do also transit spectroscopy, and also to look at to study very low mass object. And in fact, this wavelength regime is basically unexplored, and so this is Terra Incognita. So this is a wavelength range where any observations will lead to new discoveries. So yeah, we anticipate that MIRI will provide transit spectroscopy for that important wavelength range from 5 to 12 micron. Okay, an example of signs. MIRI will do a lot of disk signs to probe the colors, albedo, and the grain compositions. And so, this will be used in conjunction with its chronograph. So this is an example of the simulations of disks that MIRI will see. So MIRI not only do high redshift galaxies, but of course, very local things, circumstellar disks. Now moving on to NIRISS. This is the Canadian build instrument. So basically, NIRISS, it's an instrument that is very similar to NIRCam. It has the same wavelength coverage, 0.65 micron, but it has the pixel scale of the long wavelength channel of NIRCam. So the same field of view, 2.2 by 2.2 that's a mistake here. It's not arc second, this is arc minute. And there's 2 wheels, a pupil wheel and a filter wheel, that has various optical elements that can be inserted to do either imaging or spectroscopy. We have 2 orthogonal prisms to do wide field slitless spectroscopy. We have also another prism here to do single object slitless spectroscopy, which is designed specifically for transit spectroscopy, exoplanet transits, and a very special mask here, a non-redundant mask, to do very high contrast imaging. So I'm going to walk you through very briefly through these observing modes. So wide field slitless spectroscopy. So this is very similar to NIRCam, and we have 2 grisms that provide a resolving power of about 150. NIRCam is 1,000, so this one is more optimized for high redshift galaxies, but it covers a short wavelength part, so it's very complementary to NIRCam. And we have 2 orthogonal dispersion to mitigate source crowding, and that's the kind of sensitivity that one is getting with NIRISS. Now, of course, without a slit, you're getting the background of all pixels, and so your sensitivity is lower, but you're getting everything in the scene. So, for example, for clusters, you can fit as many as 3,000 galaxies in one shot. So this is why this is very complementary to NIRSpec, which can look at an order of magnitude less object in one frame. So this is an example of our GTO program, Chris Willett in our team. So this is a simulation of this frontier field high redshift galaxies. So this is the imaging simulations at 1.15 micron. And on the right, this is the same thing with the grisms. You see now every source become a little spectrum, and you see it's not all that crowded, except for the middle part. But by adding another dispersion in the orthogonal the directions, then we can help recover very high redshift objects, but mitigate crowding problems. So that represents major programs in Canada. Canada, the NIRISS team has a total of 450 hours, and we're taking about half of that for these programs. We're going to look at four or five clusters. And this is also complemented with NIRCam imaging and NIRSpec follow-up to if we discover very high redshift galaxies, we would like to follow it up with NIRSpec to confirm the high redshift nature of the object. Okay, so just an example. This is a discovery made by Hubble of a high redshift Canada galaxy, redshift 11. So you can see the break here, which is marginally detected. And with NIRISS, we should be able to detect, that's exactly the same object. We should be able to detect these objects in about 20 hours of observations. We need to observe over 3 filters. So basically we put the grism, but block with various filters. And we double that because we do 2 orthogonal directions. Lots of potential with this mode. Now moving on to single object slit line spectroscopy. Now we're talking about observing very bright objects. So the SOS mode covers 0.6 to 2 micron in one shot with 2 orders. You can see the 2 orders here, there's some work to actually extract these spectra. And there's something very special about this mode is that you see the trace is very wide, and that's deliberate. There's a very weak lens on the grism that defocus the light along the spatial directions, but not along the spectral direction. So that allows you to actually observe relatively bright objects. So our saturation limit is around 6-8, depending on the mode. And as I mentioned, this thing is specifically optimized for exoplanet transit spectroscopy. So this is a diagram taken from our GTO program. This is showing the radius of planets, of exoplanets in Earth radius versus their mass, and those that have been, so this is an exoplanet for which we have both the radius and the mass, and the one that are circles are our program, and we're covering everything from hot Jupiters to very small rocky planet in their habitable zone. So this is an example of what NIRISS SOS will do. This is actual HST observations with C3, and this is what we expect to have with NIRISS SOS. So you can see that not only the error bars are much smaller, but we have a much wider wavelength range, and for that reasons, a lot in the community recognize the NIRISS SOS as a very important capability to do reconnaissance spectroscopy for a new exoplanet that will be discovered in the next couple of years. Okay, so something more challenging. This is the case of the TRAPPIST-1F planet. You remember these 7 planets discovered around a low mass star, an M dwarf. This is simulations provided by my colleague here, Bjorn Benneke, where you just plug an Earth-like atmosphere and assume that everything is well mixed, that water goes all the way up into the atmosphere. And so all these wiggles that you see, and And the black are simulated data points, and the blue is the model. And so you can see that if we were to have this kind of situation, we would detect it. And that only takes about 4 transits, about 15 hours worth of observations. So this is one of our prime targets with our GTO program. Okay, now moving on to the third mode of NIRISS, aperture masking interferometry. So basically, we have a mask that we can insert into the pupil plane that takes light only from several segments. It's from 7 segments, and it is such that the baselines of these of 2 apertures are actually unique. This is what we call non-redundant mask. And that gives you a very funny PSF, but if you take the Fourier transform of that, that's the kind of very regular pattern. I'm not going to go through the details of that, but the advantage of that technique is that you can probe very small inner working angle and with moderate contrast. So this is the prediction of the contrast performance we expect with the non-redundant mask. And look at the scale here. So this is only it starts from 70 milliarcseconds to about 0.5 arcsecond. It's got to 0.3. But the NIRCam chronograph and the MIRI chronograph blocks light everything inside 0.5 arcsecond. So this is very complementary to NIRCam and MIRI. Let me show you an actual targets as part of our GTO program. This is led by Julien Rameau. So Julien actually discovered that planet, was followed up by GPI, and the points you see here are actually orbital motions. And that system, we know that has a disk, and it is suspected to have maybe other giant planets inward. And the black region here is what we were able to actually, to rule out with GPI. And so if there are other planets inward, NIRISS should be able to actually detect them through this very special mode called aperture masking interferometry. And I don't have time to go into the details of that, but of course this could be applied to any other things to look at the structure of AGNs or even the galactic center. Okay, now just to tell you that there's more very briefly, and we'll go back to this with other webinars, is that we can do parallel observations. So all these modes are allowed. So when you do NIRCam imaging as prime, you can also do MIRI imaging. You can do also NIRISS wide field slit lamp spectroscopy, and you can also use NIRISS as an imaging. We have exactly the same filters. NIRISS has the same filters as NIRCam, so you can use NIRISS as a way to cover more field coverage. And finally, MIRI imaging plus NIRISS. So you can see that the Canadian instrument is a prime, it's considered a priority instrument for parallel observations. We did not have time to discuss about dithering. You remember the footprint of the NIRCam detectors where there's gaps. Obviously, you need to observe the various dithers position to fill the detected gaps, and also to improve the PSF, especially at longer wavelengths. And there's also capability to do mosaicing, to map large region of sky that are bigger than the field of view of the instrument. And finally, and this is very relevant for solar system science, we can do moving targets. So JWST can track objects that have this kind of movement in the sky, 30 milliarcseconds per second, and it will do that with this accuracy. I did not have time to mention it, but NIRISS comes with another instrument on the side of it, on the back side of it, called FGS, the Fine Gather Sensor, which is the facility that will actually guide the whole observatory. That's also provided by Canada. Okay, now just a few words. We're just close to the hour. A few words about what's coming about preparing a JWST proposal. So basically, you have to. That's a mistake. It's not March 2nd, 2018. It's that was the date about a month ago. This thing is now April 6th. So the thing is that your proposal is due by April 6th in one single phase. So it's unlike some telescope on the ground where you do a first phase proposal, and then once approved, you do a second phase. This time, I'm afraid, you have to do the whole thing, okay? So you have to think about a program, that's you, of course, a science project. And then you have to, assess the feasibility through these tools to do this. It's called the exposure time calculator. And you have to assess also when this thing is actually visible and what orient you need to use to observe your specific targets. So there are tools for this called the target visibility tool for general imaging and also for cosmography. And then once you know all this, then you have to plan your visits, and that's called this is done through the APT, the Astronomers Proposal Tool. Okay, and of course, as part of the APT, you'll have a science justification, and then you submit. So one thing I want to mention is that the actual observing time unit in JWST, this is wall clock time. So what you will ask JWST is wall clock time. Of course, the observatory is not 100% efficient. There are overheads, and typically we think we should be with an eye here for observing efficiency. We should be close to 70% observing efficiency. That is, the fraction of the time you spend collecting photon should be better than 70%. So there's various overheads that are charged to you. For example, slew time. It will take a maximum of 30 minutes to slew from one piece of the sky. You have to configure the instrument, moving wheels around, and about 10-20 minutes. Then your science exposure, which will take whatever time your programs require. Then you have to do small angle maneuvers to doing dithers. And also you have a tax. So if you require that you want to make your observation at a given specific date and time, for example, for transit spectroscopy, you don't have any choice. You have to be there when the planet goes in front of the star. Then there's a tax of 1 hour that is charged to you because of this constraint. And finally, on top of this, in fact, there's a mistake here. It's a detail, but the 1 hour tax is outside this thing here. And there's a overall when you add all these overheads together, and you add another 16%, which is sort of the observatory fee, various overheads used for maintenance of the observatory, calibrations. The segmented nature of the telescope means that sometimes you have to align the mirrors again every 2 weeks or so, and that takes time, and that is part of this 16%. But of course, all that you don't have to calculate yourself, and the APT tool will give you all these details. So this is just a screenshot of the ATC, which you can operate either from the web or as part of a Python engine. So it's a very sophisticated tool, which can you can put various scenes, not only point sources. You can put galaxies, multiple sources, and you can configure the instrument the way you like, and it will output you a smooth noise spectrum. So that's how, by playing with this, you can define the optimal integration time that your program needs. The APT templates, so that gives you for those who have done HST proposal, it's fairly similar, and there's various menus that you have to go through to define your observations, to define which instrument, and there's various templates for the various modes you want to use. Of course, we're not going to go through that today. In fact, the next webinars will go through these details. We'll go through these tools in more details and in a demo mode. Okay, some useful information that you can grab from the web. So basically, well, first of all, to mention that all JWST data will be reduced by the Space Telescope pipeline. That's in Python. And there will be additional sets of tools that will be available, and the instrument team, especially for the NIRISS instrument, will have some specific tools that will likely be more advanced than what Space Telescope will provide. So there will be various resources to do this. There are actually right now simulated data sets that are available if you want to use, you want to play with. and everything you need to know: observatory planning, policies, data, GDO programs, and now ERS programs. It's called the GDocs. This website here, and there's also workshops. There's actually one right now on solar system ending today, and there's one in Pasadena mid-December, which is really focused on proposal planning. So this will be basically exactly the same webinars that we'll do over the coming months, the coming weeks, but this one will be an intensive week of going through all 4 science instruments. And so if you're interested, you just in fact you can go to Pasadena for this. So this is the GDocs, and the way to find it is very simple. You just Google JWST user documentation, and then you can walk through all these pages. Another very useful source of information is called the JWST Pocket Guide, where you have all the information that you need for all 4 science instruments. Just Google that, and you'll get your first hit will be the actual pocket guide for all 4 science instruments. It will give you basically all the specification that I give you today in one single packet. Okay, and finally, I wanted to mention that you're not alone. There's our team here is now turning into a Canadian JWST help desk. So if you have questions about the preparation of your proposal, don't hesitate. Just send an email to that address, and Loïc and Julien and also myself can help you in preparing your proposal. So this will be our job to assist you in preparing JWST proposal. And later on, when you get data to get you started with data reductions, of course you'll have support from Space Telescope, but there will be also another level, another layer in Canada to do this. And finally, it's not yet hired, but we'll have also an outreach officer that will be there to basically disseminate your discoveries with helping out writing press release, and we want your JWST science to go to the media in a very effective manner, and we'll have another person here to do this. So, and of course, I invite you to continue to attend these webinars. Julien just showed the actual schedule. Just go to this webpage, or just jwstastro.umontreal.ca, and there's a webinar place you can click to see all these details. So that's it. Any questions? You have to unmute yourself if you want to ask a question. I'm sure you have questions, but I guess you will reserve them when we do all the other webinars.
I had a question, René.
Yes.
This is Julie. I was wondering, are the GTO targets public?
Oh yeah, absolutely. Yeah.
Absolutely.
Yeah. They have to, and this will be the same for the ERS. Right now, browsing the ERS program, I could not see the targets, but it's a question of days or at most a few weeks for these targets to be public.
Okay, great. Thank
so
you.
The ERS, again, these are community programs. Even though they were allocated to some specific team or people, there won't be any proprietary time on those. So those are data that are for grab for anybody. That's very important to mention. Otherwise, the normal proprietary time is 12 months. That applies for GTO and also GEO. So any time you'll get through GEO, you'll have 12 months before your data set becomes public. But for the ERS, again, that data will be immediately available once it is acquired.
Okay, thank you.
René?
Yeah.
I thought I wrote down during your presentation that the Cycle 1 proposals were due 2nd of March. You have
no, I'm sorry. There was the old deadline for submitting the actual proposal, but the call for proposal will be issued November 30th, in 2 weeks.
Yeah, I know, but on your last slide, it's flashing 6th of April. Is that the actual deadline?
That's the deadline for submitting a proposal. So our webinars will end the first week of April. So I encourage you right now to dive into this. Don't wait 2 weeks before the deadline. It will be too late. It's some work, and these webinars will just be. I mean, you should see these webinars as a way to help you out prepare your proposal. So
I will just correct you, Ronnie. The last webinar will be giving at the beginning of February, not April. February.
What did I say?
You said April.
Oh, sorry. No, February, of course. I've been talking too much. Yes. So essentially 2 months before the deadline. So we will go through pretty much everything that JWST can do in terms of science programs and capabilities 2 months before the actual deadline. And again, do not hesitate to contact us to help you out in preparing your. Don't get stuck, and just send us an email, and we can probably help you very rapidly. I mean, one piece of advice. I mean, you don't necessarily have to dive into the ETC immediately. You can use the sensitivity tables that are given in the Pocket Guide, and you can assume, background limited performance, scaling with square root of time. That's enough as a first cut to define, how much time you need. And then, that will give you a rough order of magnitudes of the amount of time you need to do your program. And then you can dive into the ETC. But anyway, the second webinars will be dedicated to this, to go through these observing tools. Any more questions?
René, I see that this is being recorded. Is your presentation available? Because some of my students could not attend. Will this be available for them online somewhere?
Yes, this is actually on our website. So not only the proposal, the actual presentation, but also the recording of that presentation.
Okay, all right.
So, and this will be particularly important when we go into a demo mode. So people will be able to go back and see what was done.
Okay, sounds great.
So I guess, and Loic and Julien will send reminders for the other webinars, and we could add message to say, okay, look, the webinar 1 is here, and we can do this. But mark your calendars for all these webinars. Okay, well, I'm sure this was a core dump of information, but I hope I gave you a sense of what JWST can do, and now it's for you to start thinking of what you should do and get started. More questions before we adjourn? So anyway, let me thank you all for attending, and I hope we'll see you for the second one. Thank you very much.
Thank you.
Bye-bye.